The following program is brought to you by Caltech.
Okay, welcome back. We're very happy now to have Eva Silverstein from Stanford with the longest title of the workshop, The Powers of Monodromy and Implications for the Range of R in String Theory.
Okay, let me start by thanking the organizers for this really interesting workshop at a great time in the field. I want to recognize a lot of great collaborators, including Liam, who is here, and these others written on the transparency, which include more and more people who are investigating the subject of large field inflation in string theory in useful ways. You notice that Raphael Flauger is among them and has been among us for some years. So it's a neat thing about this field, how broadly people can contribute. Okay, so can I do a single page? But it doesn't really matter. Anyway, well, I guess we'll do it this way. Okay, so first of all, congratulations to BICEP. This is incredible. Even as a dumb theorist, I can see how amazing an achievement it must have been to get to this level of sensitivity. It's exciting that it is consistent with the level we might well have from inflationary theory, although, as Andre has emphasized, inflationary theory does not hinge on that amplitude. It's a very reasonable value for it, as we'll discuss more and more. And of course, we all hope the foreground question is decidable. It seems to be the consensus, and that's exciting. It's really, truly exciting. So, as a string theorist, I can say we're used to being patient. I mean, we've been waiting for however long it's been. Since I stumbled into this field, I've been making this joke that any time scale less than the human lifetime counts as instant gratification for string theorists. So at our KITP workshop a couple years ago, I was chatting with Matthias, and he was saying that if B modes are discovered, corresponding to primordial tensors, he would read the book on string theory. If not, he would read the book on planets. So that was the discussion. So after all the hoopla started, I offered to send him the book on string theory. And it hasn't quite happened yet. Instead, I went to Amazon.com and bought my own copy of Radiative Processes in Astrophysics, which is in the foreground of this picture. But the string theory is visible back there. And I'm going to explain why there really is this connection. And it's incredible. In fact, it's incredible either way it goes that we can test these things at this scale. Okay, so just partly repeating, I'm going to start rather broadly and then get into recent results that we're excited about in the subject of large field inflation string theory. Okay, so inflation is, as of now, our only controlled paradigm for early universe cosmology that produces the density perturbations, the seeds for structure that are, phenomenologically not only viable, but match the data in a beautiful way. And this is already true independent of the tensor modes, which would count as a further smoking gun signature of inflation, which we're all also very excited about. However, since I do think inflation is very compelling and pretty much the only game in town, to me what's actually at stake is this lever to high energy physics that this detection is related to. In particular, the genuine observational level to quantum gravity. Personally, I couldn't care less what V of phi is, except insofar as it's connected to other interesting physics. In this context of R that is bigger than 0.01, if that turns out to be the final consensus, then the subject is what we call strongly UV sensitive. It's genuinely sensitive to quantum gravity corrections at a level that pretty much everyone agrees is very serious. So I'm going to try and explain that. I'm going to start with the generalities of that to try and explain to everybody who's interested in where, to basically belabor this motivation to make it very clear. And then we'll come to string theory, which is our best candidate for quantum gravity, although we don't know what the right theory of quantum gravity is. And there we find a very simple and rather ubiquitous mechanism that generates large field inflation and hence a tensor signal. There may be others, but this is a very canonical one, which I will try to explain in a more general and systematic way than we have done before, where there's a lot of focus on very specific examples. And then at the end of the talk, I'll give some more very specific examples, which are fun and illustrate a range of different possibilities. But just before I get into any of this, I want to sort of give you this sort of picture of the difference between what you might naively think if you consider the problem from the low energy point of view and simply parameterize your ignorance of quantum gravity, which is a fine thing to do. This is what a lot of sort of quote unquote bottom-up theorists did, which is to say, okay, suppose we get we're supposed to get large field inflation, then you're talking about this large field range, and knowing nothing about quantum gravity, you might say, as you move each Planck distance, or maybe even less in field range, you might encounter new degrees of freedom that come down in energy, things that couple to the inflaton. When you do this kind of short distance completion of gravity, as in our experience in particle theories, you might expect new degrees of freedom to come in. That certainly is the case in string theory, that there are new degrees of freedom. And you might have a picture like this, with basically random stuff happening to you, on short ranges of field in the potential. And generic such random things would spoil the flatness required for inflation. However, in a large sector of scalar fields that we have in string theory, the situation is much, much more regular than this. There's an underlying periodicity, a branch structure in the potential. On each branch, the field range goes off to large values, only cut off by getting up to high energy density scales, well above the scales we need to model inflation, and not cut off by anything sooner than that. While at the same time, this underlying periodicity makes regular, gives a much more regular picture of the spectrum of other degrees of freedom that come into the physics. So a lot of the physics is very periodic on a short field range, while at the same time the scalar field itself goes off to a large field range. And I'm going to try and explain this again in terms of the rather ubiquitous couplings between fluxes, sort of our generalizations of magnetic fields that we have in string theory. It is all about magnetic fields, we all know that, to these so-called axion fields. Okay, and as I say, then I'll finally get to some new specific examples where we dot the I's, cross the T's, and give some additional proofs of principle of this more general mechanism, among which, so these add to the linear model that's been the focus in this area. Okay, so let me start though with, if you don't mind, with some more general philosophy to motivate this, because it is a special opportunity, and I want to be clear about where it's coming from. So certainly inflation and the density perturbations can be modeled, described in low energy quantum field theory. There's no question about that. The kinetic energy in the field is much smaller than the potential energy, which is itself parametrically smaller, or let me just say much smaller, even if we're at high scale inflation, than the Planck energy density. So these calculations are under control in that sense. But these don't provide a complete description, and this is related to the famous fact that gravity is not complete at high energies. The effective strength, which you get just by scaling energies into the Newton constant coupling, grows with energy, so the system becomes strongly coupled at high energies. And let's discuss this in some generality. So at short distances or high energies, quantum effects become important. This can affect cosmology in different ways. The most extreme way it could affect cosmology is if we went all the way back to some short distance singularity in the far past. And this would be a fantastic thing to get some handle on, both theoretically and observationally. That's not how it works in inflationary theory. That doesn't mean it's not a possibility, but there isn't any known controlled example of such a theory, which gives viable phenomenology. nonetheless, there have been very interesting, creative, and valiant attempts to find alternatives to inflation along these lines, and it's still an interesting question. So there's much to do to understand what came before. Let me just state that there's a lot of interesting theoretical questions there, but come back to the sensitivity to quantum gravity that I'm talking about with regard to the bicep measurement. So we think about low energy general relativity. So here is the Einstein's equations of low energy general relativity. And as I just discussed, it breaks down at high energies, where energies, at least by the time the energies reach the Planck scale. And in studying the theory of how this works as we move up in energy scales, there's a standard way of organizing the problem in terms of effective field theory, where you take the action that gives you the Einstein theory as its equations of motion, and you add to it, you parameterize your ignorance, you add to it terms that involve higher energy physics, higher powers of the curvature, higher powers of the field and its derivatives, suppressed by some mass scale, the scale of new physics that could come in, up to and including the Planck scale. So this is how one just can work parameterizing one's ignorance from the bottom up. Okay, so this is important for inflation, even though we're not going all the way back to some extreme singularity, because of the fact, which is I think now very well appreciated, that the so-called slow roll parameters are sensitive to Planck suppressed contributions to the effective theory in this sense. Okay, so even if it's a small field inflation model, it has some residual sensitivity to quantum gravity in this way. But this sensitivity is really strong in the case of large field inflation. So here's the famous chaotic inflation model of André, which many describe as the simplest possible model of inflation, which seems quite accurate as a description. The only thing it's missing is then what do you say about the cosmological constant? But so what? It's a very simple model of inflation. It gives better and better flatness of the potential in the right sense at larger and larger field range. And it inflates starting from about 15 Planck units in field space. And this is an example of a more general relationship, the so-called Lyth bound. Bound is a bad word, but it's a relation between the field range of inflation and the tensor to scalar ratio. Now, this model and others like it are completely internally consistent as bottom-up models. Its quantum corrections are small enough. It can be thought about in terms of the approximate shift symmetry along this direction, although the potential breaks it. That's a weak enough breaking of the shift symmetry that the whole thing is completely controlled from the bottom up. So the idea that inflation theory is fine-tuned is just a myth. There's nothing to that statement, and that understanding goes back to the very first models. Okay, so here's a Lyth bound again. It comes from taking the number of E foldings, which we can write as integral dA over A. We can use the chain rule a couple times to write that in terms of Hubble dt over the course of inflation. Trade that for the integral over the field with this prefactor that just comes from these various steps of the chain rule. And this factor is the inverse square root of the ratio of tensor to scalar perturbations. And so if everything is varying slowly during inflation, you can take that out of the integral, and you get this right-hand side, and that's it. That's the whole argument that gives this relation. If you put in the numbers, you get this statement about super Planckian range. Okay, so that's where we are if indeed bicep 2 is confirmed to contain a primordial component, which I would still bet on, although of course we have to wait, and I am a patient string theorist. So the statement again about the UV sensitivity is the following. So this is the equation that goes along with that picture of the random stuff happening to you everywhere on field space that I had on this transparency, which I also reproduced there. So this is just saying these corrections suppressed by the Planck scale itself, which is the most conservative thing to put in there. there would be an infinite number of these terms that would matter, an infinite number. So in theory language, we call this an infinite set of dangerously irrelevant operators. Operators that, because the field goes over a long distance, even though they are formally irrelevant, they're suppressed by some M Plancks here, they become important in the dynamics. Okay. All right, so because of this, most people believe that it really needs to emerge from some theory of quantum gravity. Even though you can control it with a symmetry from the bottom up, unless you have no curiosity at all, you want to know whether such a symmetry exists in a quantum theory of gravity. And so this is the challenge and the opportunity. Okay, so again, this was the sort of straw man prejudice from the bottom up. You can just declare there's a symmetry, but that's a strong statement about quantum gravity, even at the classical level. Okay, so I guess I've already said these things, and I want to emphasize them again. It's a perfectly good paradigm in field theory. It's just that nonetheless, it's much more satisfying, especially in the high R regime, the detectable R regime, to obtain it in a way that can take into account the quantum gravity effects. Okay, so and if we were all talking about some other field like condensed matter physics, you could ask an analogous question. You could say, suppose we consider some effect like the melting of a material, which is highly sensitive to what the UV lattice is in the material. Although you could model things like that, or even transport, which have to do with irrelevant operators, in some low energy field theory, no one would just do that. One would instead insist on working with the ultraviolet theory, which in that context we know to be basically QED with the lattice. And if you work in that field at all, you quickly learn that you can do a lot of work from the bottom up. You can parameterize different possibilities for transition temperatures in superconductors, et cetera, et cetera. But what we actually see in nature is clearly highly constrained by the fact that it has to emerge from the correct UV theory. And this is just an example to illustrate that in the context where you know the UV theory, you would be crazy not to use it in a situation where the whole thing is this UV sensitive. Now, the obvious difference is that we don't know what the theory of quantum gravity is, whereas we know QED, but that's a logically different point. That is really a logically different point. And okay, so string theory is a good candidate for quantum gravity. We don't know much about quantum gravity. We don't know anything about quantum gravity empirically before we get into this bicep stuff, which is one of the huge opportunities and implications here. But thought experiments and mathematical consistency and so on are extremely powerful in theoretical physics. And that's the basis for the huge effort that many of us make in this direction of string theory. So let me just quickly list some of these motivations, just again to set context broadly. So, black hole thermodynamics, these beautiful relations between entropy and area, the Hawking temperature, et cetera, in calculable examples in string theory come out on the nose with calculations of statistical entropy that reproduce the predicted gravitational entropy. The theory is UV finite. It resolves many types of singularities in situations that we can understand. This black hole stuff led to this amazing holographic duality that is what you hear a lot about in string theory lately. And there are just intricate connections among different limits, the famous dualities, that show us that the theory hangs together in very subtle and intricate ways. And one aspect of this is the landscape of vacuo, which has been, came as a surprise to at least some elements of the community. But I view it as actually another success of the theory. I mean, I'm kind of intrinsically an optimist, but I view it as a success of the theory. It fits with the only known explanation of the cosmological constant. It had to be forced on the theorists, but it's where we were led by the theory. Of course, Weinberg predicted this in the 80s, but he was pretty much alone. Well, a few others, sorry, Andre and others had similar ideas, I should say. So I view that as a success. One thing I want to emphasize about it, though, is although it's not as constrained as the QED lattice of the condensed matter system, perhaps, because there are different possibilities in this landscape. Nonetheless, there's a lot of structure. It's not that anything goes. There's a huge amount of structure. You can't just write down, V of phi and go home at all. And so that's where we live. We live in this interesting middle ground between there being a lot of possibilities, but also a huge amount of structure and constraints. Okay, so that's why it takes us a while to say anything. So there's a lot of ways in which there is structure in the theory, most of which I won't describe here. I kind of alluded to some of them earlier. But the ones that are more relevant for this subject we're talking about is axion decay constants are sub-Planckian in the controlled regime of string theory. I think Liam will say more about that and some recent updates of that. There's no such thing as a hard cosmological constant, although we find metastable solutions that mimic that observationally. In extreme limits of our space of scalar fields, one finds light degrees of freedom, and we'll come back to that. This is something that Oguri, Hiroshi here, and Bafa thought of as a possible connection to the question about large field inflation. And again, we'll see why this regular picture in axions more or less does not realize this, although it does in a sort of residual way. And because of these structural constraints that I'm alluding to here, I personally expect not a continuum of possibilities of R and NS. I expect some kind of discrete, what we call a discretuum in the landscape business, some discrete values. And we're only starting to map that out. I mean, we have this linear model that's been around for a while. And since BISEP, we actually developed a whole new set of examples that gave, as we'll see, another few discrete possibilities. But it's a complicated game. Our magnetic fields are also complicated. But okay. Okay, so let me finally start getting to the substance of this. I apologize if that sort of generalities were a little too obvious, but I just wanted to lay them out. Okay, so let's come to this structure that I want to focus on, which is known as monodromy. It supports large field inflation. It generates a primordial gravity wave signal. And it really is all over the place in string theory. The mathematics of string theory that people have studied since they started considering these compactification manifolds included this effect of monodromy as you go around certain places in field space. The spectrum rearranges itself in a certain regular way. And so this is an application of that very basic part of the structure of string theory to inflation. So it's all about B modes. So there's this, so in electromagnetism, we're familiar with the Maxwell theory, which I've actually written here in a spontaneously broken form. But this is the Maxwell action of electromagnetism. And of course, one writes it in terms of some potential field A mu, which is sourced by charged particles. And in string theory, there's a similar potential field that is sourced by the strings of the theory. So there's an analog of the vector potential of electromagnetism, which is instead a two-form potential field BMN. And there are analogous fields which are sourced by the higher dimensional branes of the theory as well. And axions come from integrating these potential fields over sub-cycles, sub-manifolds of the extra dimensions. So for this BMN field, it comes from integrating B over some two-dimensional cycle. Okay. So the structure that comes in has to do with a generalization of the Maxwell action in this kind of symmetry broken form that may be more familiar. So on this side, we have a massive vector field that, A mu, with a Lagrangian encoding the symmetry breaking, which is gauge invariant because when you do the gauge transformation of A mu, it's compensated by a shift of this scalar field theta, also written here. So this is a standard low energy way of writing such an action. And basically what we get in string theory is a glorified version of this all over the place with this kind of structure appearing more like what I've written here, where there's some F that's a higher dimensional analog of this d theta, plus B, which is a higher dimensional version of this A. And these descend in 4 dimensions to fluxes coupled to axions. And this whole structure is also invariant under a nested set of gauge symmetries, much like this one over here. And really, it's as simple as this, just glorified. And we are interested in how it's glorified. OK, don't worry about the technical stuff here, except maybe there are some string theorists who might want to know what I'm actually saying. So we start with a type 2 action in higher dimensions in string theory. Let's say we choose to work in 10 dimensions. And then we have an action which has a curvature term, an Einstein term, and these field strength terms, both for this B field that is sourced by strings and for these other fields. So these generalized fluxes, F twiddle, have both ordinary field strengths and direct dependence on the axion. So back here, the thing to notice is, which I should have emphasized already, is this term is totally gauge invariant, but it exhibits direct dependence on this potential field, in this case, direct dependence on this B field. And that's the monodromy effect that we'll see. It's that the potential energy grows as you move out in that direction, and it grows without bound until you reach some high energy density scale. But in a way that's completely consistent with the symmetries of the theory. OK, so we have these effective actions of the various types of string theories and a set of these field strengths, which are gauge invariant, including under these nonlinear transformations where some of the fields shift. And for the string theorists in the room, I'm talking about being general enough about that to include the couplings that we get by various reductions and T-dualities of the type 2A action with the field strength, F4 tilde, which includes, F2 tilde includes a term directly depending on B and S, and the F4 tilde includes a term going like B wedge B, and that gets squared. So there are, as does this, so there are terms that are quadratic in the underlying axion and terms that are quartic. But these fields also all couple to the other scalar fields, the moduli fields of the theory. And the adjustment of those comes into the ultimate answers for the shape of the potential and the predictions. So, but that's where we're going. So anyway, there are these terms. And the thing we're focusing on now, aside from laying this out more generally in our last paper, is to also pay particular attention to these terms that start out quartic and see where they end up in terms of the final predictions, like I said. OK, so the structure then, when we reduce to 4 dimensions, is of this schematic form. There's flux quantum numbers times axions coupled to moduli fields, these other scalar fields, like the string coupling, the volume of the extra dimensions. These are all dynamical fields. And there's a piece of the potential that is the candidate for supporting inflation. There's the rest of it that's normally just used to stabilize these moduli fields. And they can play off each other in nice ways. But again, what you see from this immediately is that if you move out in the axion direction, this phi is directly related to B. If you fix the flux quantum numbers, you just go out on some branch of the potential forever, according to this equation. But the whole structure is periodic. If you go by 1 unit in B, that can be absorbed in shifting a flux quantum in a compensating way. That is the underlying periodicity of the entire theory. And that also is what causes much of the rest of the physics to remain the same as you go along this large field range. So there's a much less fancy way of describing this, which probably everyone has seen, which is as like a wind-up toy. And I think I have that picture somewhere. OK. Okay, so that's that. Yeah, and then, so there are, okay, so there's a spectrum that you get from the brains of string theory wrapped on the cycle that gives us the axions. Those things are just periodic. As you go around once, the spectrum comes back to itself, much like the potential would if you jumped from branch to branch. There are other sort of residual contributions to the spectrum that vary mildly as you do inflation. So this is the closest thing we get to the Oguri-Vafa story. But much of the physics respects this underlying periodicity. Okay. Another thing that is sort of, simple, but which we're only now doing, is to let the inflationary potential energy help in stabilizing the other degrees of freedom during inflation, as opposed to modeling inflation as a subsector in an already rigidly stabilized system, which is the way we insisted on doing it in the past. And it's, this is not a deep point, but it's more economical and simpler and easier to control, really, to let them work together. So that's another related part of these new examples, as well as some examples we described in terms of this flattening effect of adjustment of heavy fields in more general terms before. Okay, so that's the idea, that's the structure. Now let me shift to the canonical inflaton field. This is the phi that you usually see in the model, low energies via phi. It's related to this axion, which has a periodicity 1 by some so-called decay constant f, which is a parameter of dimensions of mass, which when we work it out from the kinetic terms of the theory, in the controlled limits of landscape, turns out very sub-Planckian. So this underlying period is sub-Planckian, but the overall range, again, on any branch is larger. Okay, so if we write things in terms of phi, the canonical field, then the potential kind of takes this form. And here I've included the higher powers of these generalized field strengths, which come automatically with suppression factors of the string coupling and inverse length scales of the system. As fluxes dilute, it becomes weaker, and as the string coupling becomes weak, it becomes weaker. And these purple terms are, nicely, again, they just automatically in the theory come with these small coefficients. So it turns out to be completely accurate to drop this purple term, focus on the largest term at large field strength. Taylor expanding, by the way, is not the thing to be doing at large field strength. There's no reason ultimately to expect a monomial potential with an integer power, because we have all these other degrees of freedom that need to be consistently treated, stabilized, these chi fields I keep talking about, which include the size and the string coupling, which are dynamical. And the way that shakes out will lead to the final answers for the sort of overarching shape of the potential. So in other words, we start with some terms that look like b to the p0 or phi to the p0, but times some dependence on these extra scalar moduli fields. And then, when one includes the full stabilization and let those fields adjust as the process continues, typically we end up with still a power law potential, but with this power p not being smaller than this p naught, because these other fields adjust in an energetically favorable way. So it's very intuitive. And this description I'm giving is one way we already had understood the linear model that has been a lot of focus as a flattening effect from a quadratic potential. It can also have a direct understanding in terms of the brain physics involved, but it's a flattening from p0 equals 2 to p equals 1 in that case. Now, the rest of the stuff, the underlying periodicity, leads to other effects that can be sinusoidal in the field. So that gives us, at some level, these oscillating terms. And there, the amplitude of those oscillations is very model dependent. It's sort of like what Andre was saying about tension modes and inflation. These could be there, they don't have to be there. If one if this big lambda is large enough and these are detectable in the data, which is something people have started to look for, it would be fabulous. It would be as close as a complete smoking gun of this type of mechanism as we could get. But the thing that's model independently predicted is a large detectable value of R. So this is an extra opportunity that we'll be very interested in going back to. In fact, this is something that, so Liam and collaborators, we thought about it in our first paper, but actually Flauger and Liam and others worked out the details of this kind of signature. And we were all going to go back to figuring out exactly how F changes with time and lambda changes with time, or seeing if we could be systematic about that to help with this. But then Raphael kind of stopped talking to us about that. He was busy, but I think maybe we'll come back to it now. Okay, so anyway, maybe this is I don't need this, but this is a slight summary. On each branch, we have this large field potential. It's flattened from its initial power law at large fields. It's got underlying periodicity and at some level extra oscillations. Shouldn't be a surprise that we land on these interesting powers other than 2 or other integers. Another way to think about it is just as a spiral slide, if you want, where again we have a large field range, but other conditions remain largely the same. So our original specific model of this that led to the linear potential has this sort of dual description in terms of what's essentially a fancy version of a wind-up toy. So that's another way to think about the whole thing. So in this picture, if you erase the red stretched thing and you just move the blue endpoints, which are no longer connected, around this circle, that is obviously periodic. If you connect this with the red thing, then it's not. But you could go around once or just shift by 1 the number of windings, and that's the structure I described before in more general terms. Okay, so this has element. It's a what we call a UV completion of inflation. It shows how large field inflation emerges from quantum gravity in my view, in a rather mathematically nice and simple way. String theory knows how to do that. To me, this is one of the things that string theory threads the balance between the different requirements in a nice way. I mean, I think the theory kind of knew how to answer this question, even if we didn't for embarrassingly long. The theory did. It has elements of certainly of the older bottom-up, the original pioneering ideas of Andre, chaotic inflation. In fact, we presented this as his 60th birthday present, I think, years ago. So it's the gift that keeps on giving or taking, as we'll see. Anyway, but it's also got elements of this interesting idea of natural inflation, although, we complain about the presumed large decay constant in that. The idea of the shift symmetry and all that was for Axions was introduced by these guys earlier. And the residual model-dependent oscillations are the residual element of natural inflation that survives here. Okay, so again, for string theorists, this is all well known, but I just want to emphasize that these axions are just all over the place in our space of fields. So string theory has a lot of baggage. Many of us think part of the reason for that is needing to get the cosmological constant at least tunable. It fits with these old ideas about that, but it means there's a lot of degrees of freedom in the theory. There's a lot of degrees of freedom from the extra dimensions, et cetera. And many of those scalar fields are axions. This potential for the strings I mentioned is just one of a whole sequence of such fields, with ones that are sourced by the higher dimensional branes, for example. Again, string theorists are used to talking about monodromy and complex structure moduli space, and this is a dual of what we're talking about in some sense. Other degrees of freedom in certain circumstances can play a similar role. So I mean, if you we don't know the measure on the multiverse or any of that, but certainly if you just count fields and look at the sort of proportion that look like axions versus other fields, it if you stick with low energy SUSY, which many people are optimistic about, I'm less, I don't think that's at all inevitable, but I think it might go the other way. But in fact, even if you do that, they're roughly half the fields. If you go to more generic limits with less supersymmetry, the number of axions actually blows up exponentially in the total dimensionality of the theory. So people pick d equals 10 to have supersymmetry. If that's not the case, there's no real reason to stop there. And so axions are all over the place. And so we don't know, we don't have a definite prediction from string theory of what R should be or whether it should be large or small. But this idea that had been around that it prefers small r was kind of outrageous. It was based on some very interesting pioneering models of inflation, but not based on anything more than that, basically. And so just to make that clear. Okay, we can talk a bit more about sort of substructure in the phenomenology. Since I've just said there are lots of axions, you might ask, why am I focusing on a single axion direction? And in some sense, that's just for simplicity, but perhaps the generic case is, both this inflation idea, which I cited earlier, and this, for each direction, there's generically this monodromy effect, so you can put them together. And that tends to sort of centralize the tilt, actually. Somebody asked us about this a couple of years ago. This paper came out after BICEP, but it actually wasn't a post-BICEP effort. It was just a delayed release. Anyway, it's amusing because if you take these power law potentials that I mentioned and you consider instead multiple fields at once, then you tend to live on the steeper part of each of the parts of the potential, and that kicks the tilt a bit more red. And similarly, if you start from inflation, which presumes basically a quadratic potential, and instead you let it flatten to these weaker powers, it moves it to the right in this picture, okay, for what it's worth. Okay, so now let me come to these new examples that we put out just, I guess, last night or the night before, the first day of the post-Flauger era, in the post-BICEP era. It's okay. I'm used to working on this subject when it's not popular, so I'll just keep, I'm just kidding. It should still be popular. So I've got to shut up now. I'm still very much betting on it, not that anyone should care. Okay, but I am taking bets still. So so now let's get down to business. I've said this many times. String theory has all these extra moduli fields, which we need to treat carefully. Now we're doing that in a more economical way by letting the inflaton field potential help in stabilizing moduli during the process. So here's an example. I'm going to do first a warm-up, and then I'm going to basically describe how it generalizes to a full string theory class of models. So we're working with these terms that I tried to describe earlier that have direct dependence on this B field potential that leads to axions. And we're focusing on the ones that start out within the 10-dimensional string theory with the highest power that's relevant, B wedge B squared. Okay. Again, for string theorists, this is something one can derive from a simple Schurk-Schwarz reduction of type 2A on a circle, and this is just T duality. Okay. So let's consider the simplest extra dimensional geometry we can take for this warm-up example, where I will exhibit explicitly this flattening effect I keep mentioning, where the geometry of the extra dimensions adjust during inflation flattens the potential. Okay, so here's a torus, just a product of circles, fluxes, and axion fields, which come from these higher dimensional field strengths are magnetic fields, and these potential fields integrated over the extra dimensions. So that gives us flux quantum numbers oriented in a certain way, and as I keep saying, axion fields. Okay, so then it's very easy to work out in this little toy that I set up what the resulting potential energy is as a function of the string coupling, the size of the space, And the ratio of the two sizes of the circles in each of the, so I broke this up into two tori. Okay, this is getting into what we think of as proofs of principle, explicit examples that we can really analyze to show that this mechanism can exist in a UV complete way. So that's why I'm getting so specific. But anyway, here's the potential that you get. There's some ratio U of the sizes of the two length scales, which the fluxes push on. So just think of some magnetic field in a compact space. Its energy density gets lower as the space expands. That's the kind of thing that goes into these potentials. And similarly for the axion fields. OK, so now one can work out what the dynamics of this field, this modulus field U is, which is what we call a complex structure modulus field. And it's tied to the axion by a steep potential. And so if you just take this potential in this simple example, starting from this sort of garden variety flux axion coupling, you have this b to the fourth term, you have this modulus U. You solve for U in terms of B or vice versa. Let's say U in terms of B is what we want. And as you can see from this, it's inversely proportional to B, which means the flattening effect that happens here is this would have been b to the fourth turns into b cubed. Okay, so this is an example that at this level, which is not yet complete, but at this level, it exhibits the same kind of thing we saw before, flattening from quadratic to the linear model. Now, okay, there are these quartic terms. They flatten, at least at this level, to other powers, in this case, cubic. So this is non-analytic in the original variable b squared, if you want, but it's perfectly, but again, it's analytic near the origin and flattens to this at-large field. OK, one can check that at this level, everything is fine. The kinetic terms are negligible. It was right to solve for U in terms of B. This is a complex modulus, so U varies during inflation, but it doesn't go to any extreme values where degrees of freedom become very light. We check that. This is a symmetric configuration of axions. There are some asymmetric directions that are also very, very flat. OK, so this mechanism does generalize to full string compactifications. In this case, we found it most simple and convenient to work with a product of negatively curved manifolds, so generalizing from those tori to so-called Riemann surfaces. And the upshot is that in the full stabilization, we have various choices of how to thread the fluxes and get the axions out of these circles in the compactification. And various choices of that lead to various different results for the analog of this cubic thing. So we found models in this way with potentials phi cubed, phi squared, phi to the 4/3, and another one with phi to the 2/3 to join the original example that Alexandra and I played with in 2008. Also, there are other fields that are related by dualities to which this applies kind of tautologically, from which one could probably generalize further. OK, so these are just to flash the kind of things we deal with when we do this. So these are microscopic constraints having to do with how the various ingredients in the stabilization of moduli plus inflation have to fit together. This is a picture of a very symmetric Riemann surface that we consider to do this. And then over here, I'm just including a little more of the substance of how it works when we include all the moduli. At least here I've made explicit the volume and string coupling. So there's some potential that has a 3-term structure to stabilize one combination of those, plus other terms that involve fluxes and axions through these generalized field strength terms, which depend on the complex moduli as well as on G string and V. And there are just various choices of how to distribute these fluxes and these potential fields, which we go through in the paper that we just put out. So with kind of the least amount of symmetry, or sorry, the most amount of symmetry, we find, which are the most special examples, we find one that basically takes this form where one actually needs to tune a flux number to be somewhat large, and then one gets a naive Taylor expandable potential, okay, despite my earlier arguments against doing that generally. But again, more generally, and I think more generically, instead one gets these flattened type examples. So there's a 4/3 example, and as I keep saying, other examples like p equals 3, p equals 2, which we obtain as a flattened p equals 4. So we do get Andre's original quadratic model in this way, but through this flattening effect from an underlying quartic, interaction. So these generalize this original brain-based model. So these fluxes generically couple to axions and extend their range. Brains also have a description in terms of fluxes, which makes the whole picture very unified. But in the previous example, there was a description that is quite faithful that involves this kind of brain picture that I already showed. So we get, again, these somewhat distinctive chaotic inflation-like, but with non-analytic at large field dependence on phi, plus residual oscillations again. So in our original example, each of these examples, again, being just sort of a proof of principle of this broad mechanism, this is where we sat at the time. So this is the WMAP plot at the time, which we doctored to indicate where these examples sit and where people were saying the error bars would be in, I think we said 5 to 10 years. And actually, this was 2008. So within that time, well within that time, there's been this detection of B modes at roughly the right level. And so we're all excited to see if what fraction is primordial, of course, not just because of these specific models. But now, kind of like what Andre was saying, I'm not clear on whether this model is ruled out because it has too little R, or maybe ruled out because it has too much R, or neither. It's hard to say. But in any case, we are finding it very interesting to get our, let's say, theoretical, error bar is maybe the wrong word, but our understanding of the theory blob to go along with these experimental blobs. Because as I've tried to kind of explain, we have these robust mechanisms. We then have a job to do to make precise or reasonably concrete examples that realize them. And each time we do that, we get a new specific model that makes its own predictions. And so far, it's realizing our general expectation that because of these quantized fluxes and so on, and the fact that there's a lot of structure in the theory, that the answers will be discrete. We're still finding these interesting powers, which lead to a variety of possibilities for R, but not a continuum, at least at the moment. But we'd really like to understand this more systematically. As I tried to explain it, to me, it's tied to one of the very basic mathematical structures in string theory, and that's interesting in itself. Okay, so I guess I already said this, but there's this really tantalizing opportunity for some kind of residual signature from the oscillating part of the potential, which is there at sublevel. But like with the inflationary R, we don't know the level a priori. Sorry, in these models, we know that R is large, but we don't know about this lambda in the fourth. But if it's there, it could be a very exciting, observation. So the thing we need to do as theorists is characterize much better, if we can, the variation of. So I emphasized before how these moduli fields adjust during inflation. They move when as the inflationary energy pushes on them, and everything's dynamical in string theory. So this coefficient is some function of the scalar field, as is this F. And so, these will vary at some level during the process. And so if you look for this oscillation and that's, F is varying, lambda is varying, even if it's there, it'd be sort of hard to see unless you get that exactly right. And so it's not clear that we have few enough parameters to make that a possible to do a statistically significant detection of it, but it's something that it seems we should clearly get back going on. So we'll see. Okay, and again, our broad goal is to do this as systematically as we can. I mean, we're kind of inspired by the beautiful results about the low energy effective field theory, which packages the pioneering works on perturbations in a nice, simple way. It's harder for us to be that systematic in string theory with our current level of understanding, but as I tried to get across, nonetheless, there are these structures within the theory that we understand pretty well, and that we can, I think, do much better to characterize in a systematic way as they apply to large field inflation. So maybe that's a good job for while we're being patient. We'll see. So let me stop there.
Thanks, Eva. Any questions?
So this was to try to see whether string theory can actually generate parametrically large trans-Planckian excursion of inflaton field. And so for example, R equals 0.2 or so, do you really need parametrically large construction, or could there be some specific example where you can work out 2 pi's and those numbers to give the...
I think what you're alluding to is the fact that let's assume, as I suspect, that a primordial component will survive Bicep's discovery, and then we're at high scales as well as this large field range, and even though these potentials are a little bit flattened compared to their fiducial power law values, and they're flat enough for inflation, they eventually reach an energy density that's high, and so if you match to the even if you just match to the temperature power spectrum, but certainly also if you match to the R, it's never going to be parametric just for the reason I said, that right. You'll reach Planckian energy densities. And of course, in Andre's m squared phi squared model, he also draws it up to the Planckian energy density. There's no way to, so it could be parametric theoretically if we just, as an exercise, if we just dropped the scale. So we weren't running into that and kept dropping the scale as we went out larger and larger in field range. And I suspect that is possible, although it's not something, because we're very data driven, it's not something that we actually did. I'm not totally joking. We didn't, we thought a little bit about just the conceptual thing of whether we could get out to the range of eternal inflation. But, and okay, is this what you're trying to get at, or I mean, it's
yes,
so yeah. So we're talking about powers. I guess I should have included that here. I forgot. In the paper, we, for example, more specifically checked in this class of examples. What are the values of G string and L that you need to, and they're factors of a tenth or something. So that's the control parameter is a number like a tenth, but it's still comfortably controlled numerically. It's not order 1, but just for the reason we were talking about, there's no way it's going to be totally parametric just because you'll hit.
So I have a specific question about one of the specific model, which is your monodromy inflation example.
Well, sorry, these are all monodromy inflation examples.
Okay.
The original.
But specifically in the sense that the specific computation that you did in that context. So you pointed out that so there is a pathway that goes sort of where the scalar field makes parametrically large excursion beyond the Planck scale, but the whole spectrum should be periodic. So that means that as the scalar field make long excursions, there will be increasingly large number of lower energy state. And
well, sorry. So part of the spectrum is periodic. The part that comes, since among friends we can say what we're talking about.
Yeah.
So, there's some cycle with
Right.
with an axiom from a B field. So
What I
if
meant
you're up brains on that cycle,
Right.
that spectrum is periodic. But what is not periodic, which I think is what you're getting at. Let's go. Actually, let me go back to the picture
Right.
here. So that what's not periodic are the modes that, I mean, these are not really necessarily totally stable modes, but the modes that live on this red,
Right.
let's say D4 brain. And so as you go out, definitely those slowly as you go out, because you're doing slow roll, slowly as you come back in, let's say. So you start out somewhere where they're, they have a finite mass, and we check that they're light enough where you start. And then as you unwind, they get heavier, right? But I agree with you. I think what you're saying is as you go out further and further, they get lighter and lighter. And it's some relative of what you and Kamran said, but it's not. The only distinction I'm making about that is just this is not going out to the extremes of, say, large radius or large complex structure or something. This is
Right.
these things are becoming light for their own reason.
But the other question I had was that if you look at the figure at the bottom of this, so as phi becomes larger and larger, so the potential goes up linearly, and then but you have sort of a background periodicity, so that means that there are states whose energy is much lower than that as well. That can potentially decay into.
Oh, sorry. Okay, so how light so the periodicity, how light they get has to do with. That's the thing I was calling model. It's related to this big lambda I was calling model dependent. So in this picture, how light those things get depends on. So I think what you're saying is, okay, there are things that slowly get lighter. We stop. We start the process where they're light enough, and then they get heavier.
Right.
Separately from that, there are degrees of freedom that every time around could get light. Okay. And there's a regime where those go through massless and you produce them. This led to this trapped inflation scenario with Leonardo and so on. There's another regime, which in this picture is where these blue things are separated, where although the spectrum is periodic, they never get very light. Okay, so that's why it's that question is interesting but totally model dependent, as you can see from this picture. So if you
so in this particular model, it's protected. Is that?
In this particular, in this model, where these are far enough apart that these are a tiny effect, and indeed that's why. So in fact, in this example specifically, it was exponentially suppressed effect. But we could talk more.
Other questions? All right, let's thank Eva again.